Okay, so this problem is rectangular pasture from the December 2020 contest. So the main idea of this problem is given n cows on a grid, or just n points, however you want to look at it. You have to figure out how many subsets of those points we can create where the points, when created as a rectangular, are parallel to the x and y axes. Yeah, so just distinct subsets that we can create using those points. So I don't actually have the actual sample input drawn out, but this is just a random example. So say we're given something like this. Let's just look at how we can create a distinct subset of a rectangle with the points. So if we choose, for example, this point right here, we can do something like this, like that. That's distinct. Could do something like that. That's also distinct. And then of course, like this. As long as the points are not reused. Something like, so as I said earlier, this is a subset. This though it still matches the criteria. It's parallel to the x and y axes, and it passed through some points. Actually, it doesn't need to pass through points because I'm pretty sure they said that. Let's see. Yeah, empty subsets are counted. So it matches the criteria. The only problem is that it's not distinct from this earlier subset because it contains the exact same cows or points, however you want to call them. So our goal is to find the number of those, right? So from just this one, we can go like this, we can go like this, we can go like this. There's a lot of points that we can create. So a nice approach, which I kind of demonstrated here, was kind of like just choosing one point and seeing how much you could make just from that point. So let's say we chose that point again, right? We'd be able to make a rectangle with any of these, but we might include points that we aren't sure of. So how can we make sure to how can we make sure that those points don't intersect, basically? The sets intersect. How do you make sure the sets intersect? So what we can do is maybe choose 2 points, and we'll have the second point or the first point, like either way, it's vice versa. It'll be on top. So now we're looking at we're looking at 2 areas. So the top area is right here, and then the bottom area is the rest of it. So like down here. So if we're doing something like this, what we can do is, we know we can create a distinct rectangle with any of these points. We can just count the number of ways, the number of points that are in these 2 areas. So I did draw this one here, but this one is actually just, let me see. This area is actually only to here because it's above it, right? But then it can go outside of this area, so it's only to here. And this one is actually only to here, down below to here. So if we look at this, there's only 3 points here, 1, 2, 3. So we can create a rectangle like this, and we can do something like this. That's the only thing. So it's pretty easy to tell how many rectangles you can create here. You would only be able to create the number of points that are below, the number of points that are basically the number of points in the blue area, the number of points in the yellow area. So it's just that times that. So like 1 times 2, for example. So let's try that again with another one. So let's try choosing this point. So now the areas will become everything below down here, and then everything above that one that's still in these. It still has to be inside of these, inside that. So let's choose. Let's go here. So in this case, there's still 1 point down here, and there's 3. So that's just three possible distinct subsets we can create. Okay, let's try going up 1 this time. Something like these 2 points. So actually, let's do these 2 points. So now, this area, this top one, only contains up to here, and then this bottom one contains all of this. So now we basically have 3 times 2, that's 6. So the answer to this problem would just be trying out every single possible pair of points, and obviously you don't recount like top bottom, same thing. Like you wouldn't do this one and this one, and then switch them around because it's still the same thing. So like you have to be different permutations, right? And then we just add all those up. So this is pretty easy to do in say like n to the 4th time, because you just iterate from this left point down to this where the right point was. So for example, if we had this point and this point, then you would just count the number of points above this point where it's greater than this x coordinate, but not greater than this x coordinate, and then you would count the number of points below this one, which is same thing, less than the x, less than the y, and nothing, of course, you wouldn't count anything between here. So that's pretty easy to do in just brute forcing. But if we look at the constraints again, we notice that n is different color. So 2500. That's like it's like 10 to the 3rd, 10 to the 3rd, 10 to the 4th. It's like 10 to the 12th. That obviously will time limit exceed. So let's try another approach. And of course, it wouldn't be a difficult problem if there was no other algorithm needed, because then you could there'd probably be easier ways to do this without choosing 2 coordinates and just brute forcing if it was something like 10, for example. So let's try. I don't want to explain the entire thing from top to bottom, but so prefix sums are just it's kind of like in the name, but given an array, you would just every index in the array, or every element in the array would contain the sum of all the previous elements combined. So for example, if we had like 1, 3, 5, 8, it would become 1, 4, 9, 17. So this is pretty easy on the 1D level. On the 2D level, it gets a little more complicated with the formula. So if we're given something like this, let's say something like this. We can pretty easily sum up to any point. The way we're gonna sum up to any point from like top left to the bottom to far right is we just want to, so in these rows, in this row and this row, because it's basically like 1D, you would just add the left one, and that's all. So if we're gonna redraw this again as the 2D prefix sum version, it's gonna be 0, 1, 1, and this one's gonna be 1, 1, right? But it's gonna be a little different on the inner version. So what we're gonna want to do is we're gonna add the one to the left and the one above, and subtract this one, so that we can account for both sides. So this value right here would become 2, and then this one would become, so it was 1 originally, so this one would actually become 3, because we're gonna also add the one that we're currently at. So let's actually just go back to restarting it. So we can just move to the right and then down, because it's the same thing as long as we have the first one. So we're going to add this one and then subtract this, and then add this one, add this non-existent point right here, and then subtract this one. So an easy way to do it is like coat it with all zeros if you want. You could just add zeros here just to be placeholders so you don't have any you don't access any bad memory. it doesn't make a difference. That you could just check for that also. It's all preference. So for this one, you know, of course, it's just gonna be 1 plus 0 plus 0 minus 0, so it's still 1. And then this one, add this one, 1. And then down here, it's gonna be same thing, 1 1 0, still 1. Now you could say here, it's gonna be, so it's already 1, so we're gonna add to the left, that's 2. Add above, that's 3. Minus that one, that's still 3. And now I'll go through this one a little faster. So that's 4 5. And then we can, that's just 4 because the 1 cancels out with this one. And then down here, it's going to be just 1. And then over here, it's going to be 4. And then over here, it's going to be, so 1 and then 8. That's 9. 9 minus 3 is 6. I think make sure, 8, 5, yeah, okay. I think I might have made a mistake somewhere, but you guys get the idea of it. I'm not going to go through the full explanation. So of course now you can see, like, up to this point it's 3. See, 3. Up to this point it's 6. Let's see. Like up to this entire thing is 6, right? Let's count it. Or this entire thing. More correctly. Let's see. 2, 4, 6. Yeah. So it worked out correctly. Hopefully. I don't know. Maybe dumb luck. So this gives you just like a top left to the bottom right sum. We might need some. We're gonna need like something like this, like from some left x value, some left x, some left y, some bottom y, some top y. It's not gonna be so black and white. So to find that, it's just gonna be the bottom right. So say this is like a, and we'll just like call this x y right here. It's gonna be or let's just do it like this. Let's find the sum from here to here. So we'll call this like AB. So it's going to be A of X, A of Y, and then since we added this entire thing here, right? But we don't want this portion. We don't want this portion because we only want right here. We added this, right? So we added this entire thing just now. So what we're going to want to do is delete this entire thing right here. And so to do that, we would just do minus A of, and this is A right here, right? We're going to do A minus, so this is AB right here. So it'd be, well, I mean, it's kind of confusing because of memory going downwards, but okay, it would just be like A minus 1, and then B, and then we're going to minus this left side as well here, but we don't actually count for anything extra, so just minus the zeros in this case. That's just A, B minus 1, and then we're going to add, since we subtracted, we would have subtracted this point right here twice because we subtracted this thing. And of course it's 0 here, but we still have to add it back, so that's just A of A minus 1, B minus 1. Okay, so that's how you find it. So now that we've demonstrated how we'd find the distance between like that or something like that, the points in a certain certain rectangle of the grid, I can just move on to the code. You guys shouldn't really worry about implementation because that's never really that much of a problem. I'll just go over it very briefly. So we just have normal input. I take into a points array, and the reason I do that is because these coordinates were pretty large. They're 10 to the 9th, and if we're doing prefix sums, they're gonna exceed. I think they go up to almost 10 to the 18th because be squared. Yeah, it probably would. So coordinate compression, I won't really go over that. It's kind of weird too. It's basically just like this. It basically makes it so that the points only go from 1 to n, where n is the number of points, because like all this space right here is kind of like a waste. There's no point in having that. So what we can just do is move this value. We can move the closest x value to 1 and the closest y value to 1 as well, while still saving their original positions in the array. So it kind of looks like, so for example, let's say we sort them by x coordinate. So we're looking at the first x coordinate first. And also, for to mention, I used a variable length right here. That's kind of bad practice, but it doesn't really matter. But yeah, maybe use a vector instead. So what I do is so points of 0, that's like the first x coordinate, or actually, oh yeah, okay, same first x coordinate, and I set it equal to 1, because that's the 1 to n, right? Because that's the smallest it should be. Maybe to work at 0 to, I think it might, I just that for comfortability. Yeah. So I'll sort these now by y and do the exact same thing. So the smallest y becomes 1. So if you were to look at this again, like its position in the sorted array would just be its coordinate. This is not really, don't worry about that. I mean, you can look at it on the internet. And then of course we just mark all the coordinates as like as 1, because we want to differentiate them from the ones that we actually don't want. Like if we wanted 1, 1, we don't want 1, 2. We don't care about 1, 2, so there's no point in marking it. Okay, now this is where most of the magic happens. The rest of the stuff is pretty not really that specific to the problem. So we do the thing I was talking about right here. This is where we add the one to the left, the one above it, the current one, and then minus the top left right here. So the reason I started at 1 is because I let's see, did I do, where is it? Where's my grid? Did I define it up here? Yeah, the max, so it's like 2500. I just made it 3 just to be safe. I mean, 2.5, it wouldn't really make that much of a difference. 3, I rounded it up. So basically, that's a code. I start at 1 because it's 0 indexed, right? And so all of the zeros would just be as a code. So if I access like I minus 1, it's going to access 0, which is just 0 by, I should probably do, this is also good practice. What the, right, so yeah. But yeah, I think that's implicit, but okay, yes, that's what that does right here. We're just doing that. And then right here, we're counting the empty subsets and the single subsets, and what that is like, in this example, we also could do that by just starting this at 0. I mean, wait, did I? Oh, by going up to n, I mean, I think. That's kind of wasted. That wastes like O of n time, so there's no point in doing that. You can just account for the beginning. And what I mean by that is like, you can account for nothing, so none of them. They have to account for it right here. And then just account for just a single subset. So like, just this one, just this one, just this one, just this one. Or just like that little square around it. So that's what that does. Saves us a little bit of time. And then we start at I plus 1 to make sure that we don't recheck the same point, because we started at, yeah, we checked the exact same. That doesn't, I mean, you could just do this. Oh yeah, that's what you should do actually. You would just do this. Line caps, no wonder. That's why everything was so messed up. Yeah. Okay, so yeah, you would just start this at I, and then it would recount it against itself, which is how you get the empty subset. Actually no, you wouldn't get the empty subset from there. You only get the single subsets, which saves us O of n time, right? Checking each time checks to itself. There's no point in doing that. So this is just for convenience, saving us after we read it out. And then this is where the mostly the 2D prefix parts comes in. So what we're doing is like I was saying, we're getting xy, and then we're minusing a minus 1, which is up here, and b, which is like y2. Oh, did I say I meant not mean to say b? That's my fault. This should be y. And then this should be x, and that last one should be that's correct. So because you don't want to subtract, because that would just be like doing like this stuff and this stuff. That's not good. And that's like this stuff and this stuff. That's very bad. Don't do that. You want to behind it, and then that same height as the far right one. So that's where, so we just minus the unnecessary, so like this and then like this, and we subtracted this one twice, so we're going to add it back, which is what we do right here. And then I just cast it as long because it will overflow if I don't, I think. It might not. I think they said something about, oh yeah, no, these, yeah, we have to use a 64-bit data type, so yeah. So we have to use long there. But what we're doing here is we're gonna find the 2b prefix sums, right? So up here. So so this first portion is calculating the leftmost x coordinate. So the reason we're doing that is because we're gonna want our coordinates. So we're gonna want this range, right? We're gonna want something like this, and then down here we're gonna want something like this. So we're looking for the further left x coordinate to get the left boundary. So that's like up here, or it's like basically this is like it's like this line right here. So yeah, we're looking for that, and then once we find that, we're gonna want to go as high up as we can, or it's as high up because it's 0, 1, 0, 0 is the highest, 1 is the highest. We're not going up to 0 because that's my encoding up there, so we just go up to 1, right? That's the highest point in the way that our indexing works, and then we're looking for the maximum of the two. So now we're onto the right point, the right boundary. So we're looking for the max of the two x points. Is like, say if this is 2 and this is like 5, we're looking for we want to get to the line of 5, this line right here. So once we find that, then we want the minimum of the y values to get that y value. Now the indexing works a little easier, like 0, 1, 2, 3. So we just go to this one right here. Yeah, so it's a little more intuitive. Okay. Now we're doing the exact same thing. So we're finding the minimum of the x value, same because we want the left boundary. That's like this top left corner right here. And then we want the maximum of the y values now. So we don't want this height, we want this height down here. So it's, okay, actually no, it wasn't intuitive. Well, I guess it kind of is looking at it like this, where this is, it goes, as you go down, it's the max. But that's how you have to think about it when you're indexing the arrays. So yeah, just if you think about it like just logically, it's just the max. You don't have to worry. You can worry about that when you're implementing. But yeah, it's the max of the two x and y coordinates, because we want the higher one, or in this case, lower one. So, and then after that, of course, you just want the bottom right corner. So what we're doing is looking for the further right coordinate. That's this one. This one's more intuitive because you just come to the right. So the further right corner. And then once we get to like this line right here, we just want to go all the way to n, right? All the way down to n, 0, 1, 2, all the way to n, right? Because like I said before, we don't care about how low we go as long as it's in these boundaries. So we just go down to n. And then of course we add that to our answer. For each coordinate, we count the number of points that are in those ranges and multiply them. And then that's all. That's our answer. So hope you guys understand. If you have any more questions, I guess you can leave them in the comments.